The universe is ever expanding, revealing new aspects of its enigmatic and awe-inspiring nature. A major breakthrough occurred in 1929 when scientists discovered that the cosmos itself is expanding, a realization that fundamentally altered our perception of how the universe has evolved over time. As our comprehension of the cosmos grew, we uncovered a more profound truth. The atoms in our bodies originated within ancient stars. By 1957, it was understood that the beauty of the night sky was more than a visual spectacle. It was a dynamic manifestation of the immense and powerful forces shaping the universe. The cosmos is in perpetual motion, filled with activity and riddled with mysteries we have yet to fully grasp. This raises enduring questions about our existence, why we are here, how stars and planets form, and what alternate paths the universe might have taken. However, human curiosity is often reactive. We tend to take interest in cosmic events only when they pose a threat or stir significant concern. One current example is Betelgeuse, a giant star in the Orion constellation that has recently shown signs of instability. Its unusual tremors suggest that a major transformation could be underway. Betelgeuse is no ordinary star. It is a red supergiant of immense proportions, vastly larger than our Sun. Despite being located over 640 light-years from Earth, it appears prominently in our night sky. This impressive brightness is deceptive, as that distance means it would take more than 6 centuries for light to reach it, and over 12 million years to travel there using today's spacecraft, an incomprehensible journey compared to human history. This highlights the staggering size and power of Betelgeuse, which has been exhibiting irregular fluctuations in brightness for some time. While stars may seem tranquil from Earth, they are anything but still. Stars, regardless of size, are dynamic, systems driven by complex physical processes. Betelgeuse is particularly intriguing because it is a variable red supergiant. Its brightness changes over time due to internal pulsations. These variations, occurring over periods ranging from several dozen to thousands of days, are a consequence of the star's expansion and contraction. Betelgeuse's brightness has been seen to shift significantly from magnitude 0 to 5, marking it as especially volatile. These changes in luminosity follow recognizable cycles. One shorter cycle lasts about 185 days, while the longest extends over 2,300 days. Astronomers track these cycles meticulously, gaining critical insight into the star's internal mechanics. For instance, in February 2021, Betelgeuse's brightness in the V-band fell to 1.14, its lowest in recent years, indicating a potential alteration in its internal structure. This drew considerable scientific interest. Its deep red color also adds to the mystery. The hue comes from its relatively cool surface temperature, about 3,500 Kelvin, significantly cooler than the Sun's 5,500 Kelvin. Although Betelgeuse is massive, its cooler surface results in lower energy emission per unit area, making it appear dimmer in some contexts despite its size. What's more concerning is that Betelgeuse, typically stable for a star of its type, appears to be entering a more turbulent phase. This instability is likely tied to changes in its core. Like all stars, Betelgeuse generates energy by fusing hydrogen into helium. In red supergiants nearing their final stages, the hydrogen core runs out, causing the core to contract and the outer layers to swell. This brings about greater instability. Eventually, helium around the core begins to fuse into heavier elements like carbon and oxygen, releasing sporadic bursts of energy in a process called helium shell burning. Unlike the steady process of hydrogen fusion, helium fusion is more chaotic. This erratic fusion produces energy surges that disrupt the star's structure, driving powerful stellar winds that blow away vast amounts of the outer material. These changes destabilize the star further, causing its outer shell to continually expand and contract, a rhythmic pattern visible from Earth as fluctuations in brightness. This pulsating effect is akin to a cosmic heartbeat, signaling the turbulent activity beneath the surface. To study these complex phenomena, astronomers employ two main techniques, photometry and spectroscopy. Photometry involves tracking the star's light over time, revealing patterns in brightness and enabling scientists to follow its pulsations. These observations help detect changes invisible to the naked eye. Spectroscopy, meanwhile, examines light across various wavelengths to determine the star's temperature, composition, and motion. When Betelgeuse pulsates, its spectral lines shift, revealing the inner processes causing those changes. Combining photometric and spectroscopic data allows astrophysicists to build detailed models of the star's interior. These simulations, based on principles like fluid dynamics, thermodynamics, and nuclear physics, help predict how different internal conditions affect the star's behavior. High-powered computers make it possible to test these models against actual observations, bridging the gap between theory and real data. One of the key physical processes inside Betelgeuse is stellar convection. Energy generated in the core moves outward through convective currents. Hot plasma rises to the surface, while cooler material sinks inward, creating a dynamic circulation that transports energy. These convection currents cause fluctuations in how much energy reaches the surface. When more arrives, the star brightens. When less does, it dims. This contributes to the variability in brightness. These pulsations aren't random. They follow discernible patterns that relate directly to the star's outer layer expanding and contracting. When the star expands, its surface cools and darkens. As Betelgeuse nears the end of its life, these pulsations and convective movements grow stronger. Eventually, the star will exhaust its nuclear fuel, triggering a supernova, a massive explosion marking its death. Though this dramatic end is likely thousands of years away, early indicators of such a fate are already visible. Today, scientists continue to monitor Betelgeuse's activity, its pulsations, brightness changes, and energy emissions to uncover more about the intense forces operating within it. Every flicker of light and spectral shift deepens our knowledge of how massive stars live, evolve, and eventually die, shedding light on the broader workings of the universe. Betelgeuse serves not only as a celestial enigma, but also as a valuable natural laboratory. It helps researchers test theories about the end stages of massive stars. Unlike our Sun, which has a lifespan of more than 10 billion years, Betelgeuse likely formed only 10 million years ago. However, because of its massive size, 10 to 20 times the Sun's mass, it has evolved much faster and is already approaching the final phase of its life. When it eventually explodes, it will eject the elements forged in its core, like oxygen, carbon, and iron, into space. These elements are fundamental to life, meaning our existence is directly linked to the death of ancient stars. A particularly mysterious event occurred between late 2019 and early 2020, known as the Great Dimming. During this time, Betelgeuse's brightness dropped sharply to its lowest recorded level in over a century. Initially, there was speculation that this might signal an imminent supernova. However, further studies using space telescopes, including Hubble, pointed to another cause. The dimming was likely due to a vast dust cloud formed by material expelled from the star's surface. This dust obscured the light reaching Earth, creating the temporary darkening. This event illustrated the violent and complex behavior of red supergiants. The star's outer layers can be thrown off by powerful winds or sudden eruptions driven by convection and pulsation. In Betelgeuse's case, it appears a massive convective bubble rose to the surface, cooled, and ejected plasma that later condensed into a dense cloud of dust. This temporarily veiled the star's light from Earth, offering a real-time view into the processes that precede a supernova. Although Betelgeuse has since returned to its normal brightness, the incident was a reminder that stars are not fixed points of light, but constantly changing systems governed by fusion, gravity, and radiation. In red supergiants like Betelgeuse, this instability is particularly intense, making them highly variable and unpredictable. Studying Betelgeuse not only helps us understand the future of massive stars, but it also provides clues about the eventual fate of our own Sun, albeit on a less dramatic scale. While the Sun is not large enough to end as a supernova, it will one day expand into a red giant and lose its outer layers. Insights gained from observing Betelgeuse inform our understanding. of these stellar life cycles. An emerging area of research is asteroseismology, which studies stellar oscillations. Just as seismology on Earth uses quake-generated waves to probe our planet's interior, asteroseismology analyzes vibrations within stars to determine internal characteristics like density, composition, and temperature. For a star like Betelgeuse, this technique enhances our understanding of how energy moves through its massive, convective layers. These models are crucial for predicting when and how Betelgeuse will reach its explosive finale.